agreement to hackathon here, you know, it was always difficult to drive under the sun, and so that's why we need sunglasses, you know. So our Meetup is just like sunglasses. It gonna improve your vision. Our Meetup yesterday passed 1,500 members, and our Meetup is just 6 months old. So you can see how much kind of interest people are interested in big data, cloud computing, particularly on real-time side. Today, we have a distinguished speaker, John Mashey. Actually, he has lots of titles, but two most distinguished titles. Actually, he was a former CEO of SGI, Chief Scientist, as well as a trustee of Computer History Museum. He's an active investor, and he's similarly retired. One thing I should let you know, I just studied one of his PowerPoint slides probably 15 years ago. Later, 80s, actually, he coined on big data buzzword. And actually, lots of people, they don't know that, you know. Welcome to John.
Thanks. So, yeah, I'm really glad to be here. This sort of has caused me to revisit a lot of old slides and put together some history for you. But let me start off, as I often do, by finding out a couple things about the audience here. So, how many people here are hardware people? You, okay? How many people are software people? How many people are more business people? Yeah, okay, good mix, all right? Okay, if you're a software person, or have been, think about what decade you started writing programs in, okay? So, how about 1960s or before? Okay, well, yeah, that wasn't completely before computers, all right, but close. 1970s, okay, 1980s, 1990s, since 2000. Okay, so we got a good mix. All right, let's try another one. How many people have ever used the key punch? Okay, well, we got some old timers then. Okay, so I'm going to do a little different talk than I think this meetup usually has, is that I'm actually going to take a long look at the past of big data, and in particular, try to draw some lessons from it, because when you're sort of looking ahead and trying to predict what may happen, some things are really easy to predict. Other things, particularly if you're in a state of turmoil, you can kind of find meta ideas about what will happen, but sometimes the exact outcomes are really tough, right? And navigating through that kind of period can be exciting. And I actually think we're in another one like that. Enterprise stacks are getting redone all over the place. People are investing in different companies. Anyway, it's an interesting time. So, a little bit of background on me. Don't worry, I'm not going to read all this.
If you move to the left, there won't be as much feedback.
Oh, feedback, okay. So, basically, I'm a physicist mathematician who got seduced by computing and ended up getting a Ph.D. and then getting recruited by Bell Labs. I was truly lucky. I arrived the same week as the second PDP-1145 UNIX machine in Bell Labs. And we were in a really terrific place. We had a 1,000-programmer programming organization. And I was in the software tools department. And our goal was to move a lot of people off mainframes for their software development and basically beef up Unix to be usable in a computer center to make this work. So, you know, I did funny things like kind of create shell programming and shell scripting and things like that. Okay, well, come 1983, I've been managing some great software projects, including data mining, but the Bell system was about to split up, and I decided the weather was better out here. So I came out, and how many people know Convergent Technologies? You, yeah? Okay. They did distributed workstation servers for the business market real early. But then I got scooped up to go over to MIPS Computer Systems, because I'm basically a software guy, but this was a once-in-a-lifetime chance to actually influence a new computer architecture to be what I wanted instead of the crazy hardware that I'd often had to put up with, right? And believe me, the microprocessors of that time had some of the weirdest bugs, you know, I mean, it ages you quickly. You know, I'm only 30. I mean, you know, it's really, really hard on you, right? Okay, so I did a bunch of things there, particularly relevant to the big data is I was pretty heavily involved in designing the 64-bit version of MIPS, and which came up later. And I spent a lot of time helping start the spec benchmarking effort and a lot of other things. So we got bought up by Silicon Graphics, and I had these funny different titles. I had a wonderful job that had nobody reporting to me. I could run around and stick my nose in anything. So I did anything from business strategy to spend half the time talking to customers and running around the world. SGI at that time was really a cool company. In particular, we always had customers who were trying to do things that were impossible or almost impossible, right? And those were always fun, right? So it turned out I sort of started using the term big data about 1994, and I was sort of one of the main evangelists for the company, so it ended up being a fairly major marketing theme, and I'll talk about that some later. So these days, my wife, here's my wife, Angela Hey. You should thank her, she did the food, right? She's a Meetup food guru, okay. So, why I'm here is I sort of, you know, long ago, I've not been doing big data particularly, but I got this call from the New York Times saying, we hear you invented the term, right? And I said, well, I didn't really invent it as far as I know. It's such a simple term, anybody would do it. You know, it probably came from sitting around the lunch table at SGI. But also sad to say, even when you coin a big term, there's very little coin in coining terms, okay? So, right? But what I really wanted was to get the shortest, simplest phrase to convey the idea that boundaries of what you could do with computing were always advancing. That what was big now, in 10 years would be, ho-hum, maybe 20 years, but something like that. So, anyway, that's what it turns out to be. So now I get these funny calls saying, we hear you might know something about this, why don't you come talk to us? Like this. Okay, so another reporter called me up and says, yes. Now, how has your definition changed since 1994? I said, oh, not at all. Because, you know, we'll get to that. Okay, all right. What I'm going to do then is I'm going to do a lot of history and show what I think are lessons, and then talk about what's gone on recently. Why is big data so hot right now? And then look at some things from a high-level view at where things might be going. Now, we'll have time for Q&A at the end, but go ahead and ask questions while slides are up. It may be that I'll say, don't worry, I'm going to cover that later. I'll hold it till later, but go ahead and ask if there's something up that doesn't make sense. So, here was the question, why hasn't my definition changed? Because for me, big data always was something that was beyond what was widely and easily available. And the red is what they currently call these things, right? The 3 Vs or 4 Vs, I guess there are these days. And that was, if it's beyond memory capacity or I/O performance, or it's got really tough real-time issues, or if it's complex and difficult data, as you find in multimedia, big 3D models like of a Boeing 777, you know, that's pretty big data. Big scientific data sets, these things can be pretty messy and complicated. But the other thing was, it was always a moving target, because, you know, if it fits in a memory of something that's just easy to have, well, it's trivial. Hey, maybe you put a few disks or once upon a time tape drives, that's probably pretty reasonable. Now, if it needs sort of one of the biggest systems around, or a network of them, and some stressful programming where you get surprised and it takes some specialists, sometimes a lot of roll your own software, you know, that's where I would put big. And that's always a moving target. Impossible is not even the NSA can afford it. Okay, right? You know, that's a big budget, you know, whatever it is, and, but there's still things that they can't do. So, just as a reminder, a large 1970 mainframe that would cost millions of dollars could get a whole 1 megabyte of memory. Plus, maybe 8 megabytes of kind of slow memory. Think of sort of like flash, you know, right? That's what you could get. That was a big machine, right? And of course, the high-performance cache memories on laptop chips are this big these days, right? But once upon a time, if you used up a whole mainframe, you know, and some disks, that was big data. So people have done big data for a really long time, but the labels keep changing. And these are kind of marketing functions, I think. And I was an engineer, so, you know, I kind of resisted the latest buzzword. That's why I just called it big data, to keep it simple. Right? So let me go back. Does anybody recognize this device from 1890, before all of our times? Anybody know what this is? Yes.
The tabulator and Jacquard's loom.
Yes. Okay, well, it could go back further. You could go back to Jacquard looms. But this was the Hollerith machine, the original one, in 1890 that they did for the U.S. Census, because there was too much immigration and the country was growing too fast. They couldn't complete the previous census in the 10 years. So they put out for bids, and this was the result. What they did was punch holes in cards. They put them in this thing, and little bars would drop down into a mercury bath, and then the dials would go around to count. Okay? Now, you know, there were only like a couple of these. This is one of the, I think there's 2 or 3 replicas, and this lives in the Computer History Museum. If you come over there, you can see this thing. Well, I'd call that big data. It was just pretty much beyond the state of the art for the time. Okay? Well, how about if we come forward quite a few years? Here we go, 1950. IBM 026 key punch, 80-column cards, you know. The next thing to the right is a sorter. You stick a stack of cards in, you say, I want to sort on column 1. It'll sort them, and then you go to column 2, and you eventually get them all in order. Actually, these are still around in the 60s. I used one occasionally because I had a deck of cards that were a couple thousand line program, and they fell on the floor. Thank goodness they were sequenced, so I could sort them back together. Well, you know, that was even 60s. The thing on the right is, well, I call it an accounting machine, and it would do various kinds of tasks, but the program for them is this mess of wires on the left. That is, this is a plug board where you write the program, in effect, by connecting up different wires into different holes. And the program library would be a rack of these things. And like this one was the weekly statement panel that you know, would take that out, put it in the machine, run some cards through it, print some things, and you would set a whole bunch of weird switches and things, and that was your program. Okay? These were widely used. Okay? So that's not quite big data, but about as big as you could get, because there really weren't even magnetic tape drives. I mean, you know, it's not that. Okay? So those are the good, well, I'm going to call them the good old days. When I take Stanford students around the museum, they look at this stuff and go, you guys used this stuff? You know, they mutter to each other, they used this junk, I can't believe it, how could anyone do anything? Right? Wait till you see paper tape. Okay. Well, now we come forward to, you know, one of the most successful computer lines of all time, the IBM 360. How many people have ever used anything in that family? Okay, reasonable set. Okay, so the one that's shown is actually not the biggest. It's a Model 40. It was a widely used version. This illustrates a problem, by the way, when you're not thinking big. This had 24-bit addressing, and therefore 16 megabytes of memory max. Okay, right? Remember, these were, you know, big machines, you know, for their time, right? And and it turns out, you might say, why did they do that? Well, on the lowest model, it saved hardware to not do the high order 8 bits. And the result was, all of us smart programmers said, oh, 8 bits for flags and stuff. We can stick them up there and they're safe. Right? Bad idea, right? I mean, I wrote some code, assembly code in 1970 that was still running 30 years later, and it was running in 24-bit compatibility mode because it wouldn't work any other way. Great. Right? Big machines are these other models here. We had one of these at Penn State. Megabyte of main core memory, up to 8 meg of large core storage. This one here has 36040 has 4 tape drives in the back, and it's got two 2311 disk drives, each having 7 megabytes of disk space. Okay, all right. Again, less than your cache memory on a laptop chip. Now, by 66, they were starting to get the next bigger drives, which were a whole 4 times denser. These are in the removable disk packs that you put in there, right? So if you had 10 of those drives, you had a pretty substantial system. Now, for really big data, you could get a device that would hold 400 megabytes. And we had one of these things, right? Definitely big data. What this thing was called a noodle snatcher or a washing machine because it had a tub with magnetic strips hanging down with little tabs on them. To get to data, 2 sets of fingers would come, spread the tabs apart, and a hook would come down, snatch the noodle up, put it on a rotating drum, then heads would go back and forth and read and write. Okay, right? And ours actually worked, but a lot of them leaked oil and are just broken, all kinds of bad stuff. Okay, right? But it was wonderful for 400 megabytes of disk-like stuff. Oh, it was great, right? Now, another thing that happened then, at least in IBM, that model was the first one with virtual memory. And in fact, so how many people use virtual machines at all these days? A bunch, right? Well, that's actually where they started back before 1970, right? Thing at IBM called VM, well, it was called CP67 originally, but then it became VM CMS. But this is a way a class of things happens in big companies, is there's kind of an under-the-table garage shop kind of project, but it ends up being so popular that even though the powers that be don't like it, it keeps living on and growing and being a regular product. Now what's interesting was, except that those mainframes, virtual machine ideas kind of disappeared for a couple decades because people were off building mini computers and micros that didn't do this. But so it's interesting to see it come back. Now another thing that was going on then were service bureaus. Mainframes, really big ones, could be real expensive. Lots of people, did not want to have operators and set up a machine room and buy big computers or lease them. So there would be service bureaus that had shared access where you could, they'd have a pool of machines and you could, kind of get the compute power you needed. Sometimes these days this might be called the cloud, right? Or, Amazon Web Services, right? There were certain resemblances. Very much centralized. I mean, at that point, most computers were big things. Now, this is the first of a topic. I'm going to mention these red stack wars. Sometimes during computing history, there have been wars amongst stacks, right? Where there's whole complexes of hardware and various combinations of software. The stack wars at that point were between the big mainframe vendors, each of which had its own ecosystem around it. Right? There were some languages that would work between, but others just wouldn't. Okay, right? People who use computers wanted the same languages to work everywhere, but they didn't. Okay, now, in the 70s, all the machines got virtual memory. You could even get 8 megabytes of main memory, in the early 70s. And while they weren't big data yet, often there were signs on the horizon of something smaller and cheaper that ends up growing up that turns into big data eventually. So mini computers got rolling. How many people have ever used digital equipment machines? Oh, okay, a bunch, right? So my first PDP-11 was 1145 with 248 KB of memory, 16-bit machine, and we got 16 users on it when we struggled, okay, right? We could do that. It was wonderful. Okay? And then we got 1170s up to 4 megabytes, and we worked really hard at Bell Labs to get up to 48 users on those things. That was amazing. Those are the kind of disk drives you got. Well, big leap in 1977. The VAX 11780 came out. that was, you got more memory, but it was a 32-bit machine. So now you could, you could access gigabytes of memory. It was wonderful. Even if you could, you couldn't buy it, but you could at least have the virtual memory. We always used to say virtual memory is a way to sell real memory, but you couldn't get more than 8. Okay, so now one thing DEC did pretty well, pretty early, was to compete with mainframes. They started clustering their mini computers together, right? VAX clusters, and they were, doing really well. DEC in the late 70s and early 80s was a really powerful company. Microprocessors at that point, toys. Ken Olsen, who was the CEO of DEC, once said, personal computers, who would ever want that? Well, they did later, right? But personal computers and workstations got going. Some of the wars at that point were in different algorithmic languages. There have been hundreds of different computer languages done, and things were still fighting it out. Okay, now the picture at the right has a PDP-11 with 2 guys in front of it. Anybody know who they are? Yeah, Ken Thompson and Dennis Ritchie, okay, 2 guys who did UNIX. Right? And back quite a while ago, Ken had more hair back then, and Dennis was still alive. Okay, right? So that was an early thing, and that was a little bit, I won't say a road project exactly, but they actually wanted a PDP-10, which was much more expensive. They couldn't get the budget, and the world probably got changed because of the fact it was on cheap machines. Okay, so I was over at Bell Labs. Now, the Bell system in those days was 1 million+ people, and Bell Labs had 25,000 in R&D, which is pretty huge, right? So kind of the first half of that time, I was working on the Programmer's Workbench. I used to give a talk, ironically, for this audience called Small is Beautiful and Other Thoughts on Programming Languages. The whole point was to get people to use tools, use existing software, don't go rewriting everything from scratch, use the highest level scripting languages you could get away with. And then small teams, fast iterations, move quickly, get user feedback. Does any of this sound familiar? Yeah, agile programming. Okay, right. But unfortunately, I didn't come up with a good name for it back then. So, but we actually built a project that I managed where the first iteration of it was a data mining system. It had 20,000 lines of code, 5,000 of C, and the rest was shell and awk script. Right? And we put it out in the Bell system, and in fact, the requirements we've been given were mostly wrong, so we had to move fast, right? I printed that out, dropped it on Brian Kernahan's desk, and he freaked out. He says, "What? This was a little tool. What are you doing?" I said, "Hey, Brian, it works, So, good fun." But the Bell system was into big data. It was always into big data. It was already big by the time I got there. We had to track every telephone pole, cable, junction box with geographic descriptors. We tracked every trouble report that came in off 411 calls, okay? So note the squirrels and guns? So we would know things like in what areas were there outages of phone lines due to squirrel bites on the cables, okay, right? Or where were there gunshot, okay, that wrecked phone service, right? Turns out that's mostly like in the U.S. South, some of the West, and Maine. Okay? Okay. The old Bell symbol was a good target, so they used to ship. Okay, right? So people would analyze this stuff to death. Okay, right? There was a building at Bell Labs Murray Hill where that's all they did was get phone records and analyze all kinds of stuff about where to put networks in and who was doing what and whether they should have special deals on certain days and how bad was Mother's Day going to be. Mother's Day was the peak call time. So this looks like big data to me, right? Okay, I was working for this thing called Elmos, and we had a distributed system right then already in the early 70s, a mainframe with a big database, and triplex mini computers in front of them because they always had to be up, right, to take calls and support folks. Again, this one thing was a back-end data mining system built out of shell scripts. I don't know how many people have run into Tuxedo. Run into Tuxedo? Yeah, a few, yeah, okay. So that's some transaction database middleware. That actually came out of this same project. It was an internal thing. It got turned into Tuxedo. and then as software often does, it got sold to one company, moved around, you know, and it's part of Oracle these days. Now, one of the funny things is, you know, the cloud is another big name these days. In Bell Labs in the 70s, I'd swear almost every presentation I ever saw had at least one slide with a big cloud in the middle. Okay? Right? Now, first that was the telephone system. Of course, that was the cloud. That was how everything would hook together, right? Now, there was an effort, sadly chewed up $1 billion, is the usual number, called different names over different time. And the idea was to have a mini computer network where a lot of the processing was in the network to serve dumb terminals at the periphery, okay? But there would be an awful lot of services sort of out there in the cloud. I mean, it was a cloud, right? The problem was it took way too long to build. They probably had the wrong people doing it in the first place. And by the time they were done, there were PCs, you know. Dumb terminals really weren't what you wanted to do. But it's also an example of they were trying to build an internally packet switched network that, unlike the ARPANET of the time, scaled and was cost-effective enough. Right? The ARPANET at that point, was the predecessor of the internet, was still pretty small and was pretty expensive. So it's too bad. It was too early, but that's the way it goes. So anyway, you know, in the 1980s, there was stuff that wasn't called big data, but it sure was. How many people know the company Teradata? Hey, a lot of you, yeah. Well, they've been out there a long time, right? And building big systems. So definitely a big data by my definition. They were always beyond the edge of what was in a normal machine. Right? Amusingly, they just started using the phrase big data in 2010, which I thought was sort of fun. Okay, another important thing that happened is RAID disk definitions got stirred up by some friends of mine at Berkeley, all right? And then, you know, over time, that became a standard way to do things. The important thing about that, it's another one of these things where the biggest thing gets overtaken by a collection of smaller things, right? Up until then, the big disk drive vendors were building bigger and bigger disks. What happened here was they started to use commodity disks that they knew would fail, right? And figure out how to work around that, right? And of course, that's become a mainstay of things. So, more signs on the horizon. Network stack wars during that time. I mean, the different networks were fighting it out, Ethernet, token ring, and so forth. A big deal was when DARPA funded Berkeley. They ended up doing 4.2 BSD that had TCP IP in it, well integrated, and that got used all over the place. It helped the workstation market. Lots of research got done and so forth. Then there were the relational database wars. Oracle, Informix, Sybase, etc. You know, in retrospect, we know who got to be the big dog, but it was not obvious at the time. Right? You know, lots of fights going on there. Then there were the UNIX stack version wars, right? Each vendor had their own flavor of UNIX because it was, you know, it wasn't quite open source, but it was more open than anything else you could get, right? And there were Berkeley versus System 5. There was AT&T versus OSF1. I mean, you know, it was kind of like if you ever played the game RISC. Anybody play the game RISC? Yeah, okay. Well, you know, the coalitions would change all the time. You could never tell who was on whose side. Then there were distribution wars, like between centralized and then workstations and client server and PCs and thin clients and different networks. I mean, you know, it was pretty chaotic. Then we got to have microprocessor wars. So I had fun with that, right? In particular, this is about the time that microprocessors started to get good enough to put terrific pressure on the mini computer makers who had been doing pretty well until that point. And again, first 64-bit microprocessor, we started designing it in 1988. Windows systems. There were lots of different graphics Windows systems, and now you've plotted it out, right? And if you picked the wrong stack, you had a lot of work to go back and redo. So, by the 90s, again, I was over in SGI, and we had more wars. We had browser wars. Clearly, the internet was now going great guns. The World Wide Web got going. Lots more multimedia was coming in as it became feasible. So think of that as here's cloud coming. Now, by 1992, 64-bit micros in systems were starting to happen. And by 94, actually both Digital and SGI had multi-processor substantial systems where you could buy more than 4 gigabytes of physical memory and actually use it. Right? The earlier machines tended to be a little bit smaller. You didn't really quite need it, but you were getting close, right? So, you know, our Challenge XL machines could do 16 gigabytes of memory, and, you know, there were customers who bought that, recompiled one Fortran program, made the arrays bigger, and then used all the memory, you know, the next day, right? So it got to be useful. In computing history, whenever you run out of addressing bits, life gets miserable. Particularly if you can buy the memory, but you can't address it. You get one layer after another of things that age operating system people real fast. Right? You can make it work, but it's so painful. If you want to see, there's a couple references here. I wrote this paper called The Long Road to 64 Bits because it took a long time from the first 64-bit chips to actually get software to mature enough and be used elsewhere. Okay, now, come 94, and this is a little fuzzy. The only copy I had of this was a video, okay, right, that my wife kindly digitized for me. So these are talks that I was typically given about 94, called Hardware, Wetware, and Software. How many people know the term wetware? It's human beings. It comes out of cyberpunk. Right? The idea here was, if you've got a lot of big data coming at you, you've got to manage it, but you're trying to get insight and communication out. You're not trying to just have the data. Like a lot of the old transaction systems, you had to keep a lot of data, but you didn't sort of have to understand it very much. So here are the kinds of things you needed, which just happened to be what SGI did, so that was good. Particularly big I/O at the bottom, because of SGI's high-performance graphics versions of things, we tended to need higher I/O bandwidth to feed the Mongo graphics pipes, right? So we tended to, I won't say overbuild I/O, but we built a lot of it. Okay, well, here are I said, here's the computing industry in 3 charts. Standard chart number 1, more on a logarithmic scale. Right? Got to watch out, right? Looks like a straight line, but a lot's happening up there at the right. Okay, the next one is, if that happens, the standard chart number 2 is less. That means how much hardware do you get for the same money? How much does it cost? And then the last one is performance of wetwares, us. Well, you know, so far since I've done this talk, I haven't seen any great performance increase. Although I think maybe younger folks who grew up with video games may have better eye-hand coordination than some of us older guys. And the message at the end was, well, hardware keeps getting better, wetwares don't, so software's got to bridge the gap in between to make this stuff be sensible. Now, people often know of SGI as a technical computing company, and that was true, right? And we were doing supercomputers, we were doing all these applications like these. The big data theme got to be part of our standard marketing. This was a supercomputer show, so you can see the big data logo there. A friend hearing about this dug this photo out. I didn't have it, so that was a handy thing. But you know what? We were doing other things too, like some of these other things. Particularly, you see the data bit management and data mining. Inside SGI, there was sort of a corporate suspicion of anything that looked commercial. We like technical computing. But some of us said, look, that's where the money is, you know? There's a lot of money out there, okay? So we build all the right stuff to go after it. We need to go. So we did. We also did some things like what I call new visualization. Now, these are in the early 90s. The idea was that you like at the bottom right, you could sort of fly over data. This was like flying over your file system. And the net effect was you could see how big the files or how new they were. It was like having a data helicopter. Okay. Now, how many people have ever seen this program? Yeah, a couple of you. Okay, well actually a lot of you have, because, let's see if I get this. If we get this, yes, good. Okay. Here's a minute clip from a movie I bet a lot of you have seen. She says, UNIX system, I know this. Yeah, all pre-teens could, boot up Unix systems, okay? At that time, anyway. So, they're trying to keep the dinosaurs out. She flies over the stuff to find the right stuff, okay? So this proves that, that high-performance computing and good visualization can save you from hungry dinosaurs. Okay. I'm not going to go into detail. I'm just showing the kind of stuff that I would talk about. Some hardware trends are pretty easy to predict, and some things are always problems, okay? Like in the lower left, the bandwidths inside machines tend to be a bunch more than the I/O bandwidths, and those tend to be more than the networking bandwidths. And by now, all these points have moved up some, but it's still there, right? And that's often a problem. You may be able to push the data around real fast inside, but you got to get it in and out. And if you're doing big data problems, sort of by definition, you got to work real hard on that. The worst problem is over at the right. And up here, bandwidth goes up and latency goes to the right. And the problem is that as you go further to the right, you get more capacity, but you get worse latency. I mean, like one of the truly sad things is disks are huge, right, compared to what they used to be. But the seek time and the rotation times, have barely changed. Right? I mean, I know people who sometimes only used a tiny fraction of the disk because if you seek around a lot, it gets pretty slow. Right? And sad to say, that hasn't changed. The other thing that hasn't changed was down at the lower right was bandwidths and latency of us wetwares. I mean, the only thing we do very good is pattern matching via the eyes. Right? There we're better than, still somewhat better than computers, but anything else we're not. Right? And if something happens where the human's got to think about it, it can get slow fast. Now, here's one that's also important in a business sense, is if you look at the history of any given application, over time, as computers get better, the response time goes from something that maybe runs months. I mean, I know people who use supercomputers and they run a simulation for 3 months. Okay? Okay, well, it gets better, it turns into something overnight. A lot of chip designers around the valley do that all the time. At some point, something gets to be nearly interactive. You can sort of run it, and then, you won't go do something else. You'll wait for it to come back. And then when it gets down below a tenth of a second or a second, it's really interactive. It's inside your control loop. Right? You can imagine if it took a second for a mouse to respond, it's not good. Okay? Nobody would ever use a mouse if it took a second for it to respond. Okay? Or 10 seconds. Nobody would ever do that. Okay? And what happens is over time, different kinds of applications start at the upper left and work their way down to the right. Okay? And one of the interesting things that's certainly happening right now is that as cloud and all the parallel database work happens, lots of things get much further down that curve. Right? And when that happens, there tend to be new businesses and new kinds of solutions. And that makes for interesting times. Yeah, clearly what happened to get some of the interactive stuff was cheap microprocessors, because you can at least do the local interactions at your computer. Okay, now, you probably can't read this, but I can. So here are just some of the customers we had in 1994, 95. Some of those are technical customers, but there's telecom companies, there's defense agencies, there's news companies. There's a bunch of other kind of folks in there, and then there's some more. And there's oil and gas, and there's a mix that we were just sort of getting going at that point. Now, why were we able to sell those? Because we had full-bore 64-bit systems, and people could get bigger problems into memory instead of killing themselves at trying to make lots of disks and other stuff work. So this was around 96, 97. AOL was doing a bunch. We had data warehouses. That was what we called big data at that point. I still call it big, right? We were doing stuff for AT&T. We had things for banks, right? Banks like this. Wall Street like this, right? I used to go to Wall Street all the time, talk to the rocket science crowd there, and they would crunch away and do lots of big data stuff. It's good stuff. Telecom New Zealand was one that I helped sell. This was head-on with Teradata, right? We replaced the Teradata. Good example here. They were using really, really proprietary hardware. Ours was sort of proprietary, but it was UNIX and it was microprocessors other people could buy, and it was more flexible, and so we beat them out there. Probably at this time, I don't want to talk about the last category, given all the recent news, okay? But yeah, I've been in the NSA and the CIA and the Defense Signals Directorate, all those places, and those guys have done big data forever, okay? Just by definition, right? Always got to keep an eye on them. They'll suck up any amount of data they can. Got to keep a good eye. Okay, well, you know, they used to put me up in front of a financial industry analyst, so I did that. And then the next kind of thing was this talk that I gave a lot called Big Data and the Next Wave of Infrastructure. The idea was that the explosion of data possible by having bigger, cheaper disks meant there was going to be a lot of stress on the infrastructure of networking and computer design and so forth, right? In particular, at that point, not everybody had even gone to 64-bit microprocessors, right? And so some people were still straining at the 32-bit limits. So here were the kinds of stuff we were saying. See those applications? Any of those look familiar? Yep. Right. Here were sort of later customers. See, there's a whole bunch of there that are kind of commercial kind of customers. You know, they're not what you think of as a Silicon Graphics, WYSI graphics kind of customer. Here was an application framework for that time. Gee, you know, the labels had changed, but some of the same structure is there as what you see today. Skip that one. These are some of the things that we did, and you know, some of these numbers are laughable now, right? Yes?
Can I ask a quick question? Actually, you know, right now, at this moment, comparing to a decade ago,
Yes.
The model of business, you know, as a widespread of open source model, the technology stack, the business model, as well as the venture funding model are totally different comparing to a decade ago. So,
yes.
I mean, the entry barrier to start a new business is much, much lower than
yes.
a decade ago.
Yeah,
at least, you know, several million. You know, right now, you know, a $250,000 or $500,000 probably you can start.
Yes.
So, according to your experience, you know, why SGI is back? You know, SGI definitely was at a high moment, you know, or
yes.
high noon, you know, whatever. Now it's back, you know. Why?
Okay, so I think the question is, gee, SGI had all this good stuff, what happened?
If you look at a stock price, right?
Yes. Okay, well, I'll come back to that some at the end, okay, right? But, you know, the wheels sort of came off SGI eventually, so it was too bad. Also, I would make this one piece of advice. Be wary of big mergers and acquisitions. We bought Cray Research in 1996. That was probably not a good idea, right? Because in fact, it dragged us away from some of this kind of stuff. I mean, SGI is still there. It's about $750 million. When I was there, it was about $3 billion. And as much as I like working with some of the folks we got from Cray, it was not a good idea. Right? Anyway, we did pretty substantial things for those at that time. I mean, now, you know, say back up a terabyte to tape in less than an hour, that was a big deal. Okay, right? Now, you know, nothing, right? But this is, you know, this is 15 years ago or so, something like that. Okay, so how did we get here? Well, starting in 1994, there was Beowulf. People know Beowulf, okay? These are clusters of PCs typically used in national labs and technical computing. So, not big data exactly, mostly for compute, cheap compute, but again, a sign on the horizon. Finally, by 2003, 2004, the x86 architecture got to be 64-bit. Virtual machines with VMware and others came back in, right? We got companies that scaled up or scaled out, especially like Google. Hey, MapReduce, Hadoop, all right? Lots of software infrastructure came along, and they kind of did for the relevant database apps what parallel programming techniques did in the 1990s. One of the reasons Silicon Graphics was pretty successful in the supercomputer market is we came from out of nowhere and had at one point like 250 of the 300 of the top 500 supercomputers, was we had pretty good tools for taking a Fortran program and making it use multiple processors in a good way, right? And the trouble was, early on in the late 80s, you could do that and it required super wizard programmers. Over time, a lot of the infrastructure and debugging and all that stuff you gotta have came along and people could do it. We used, you know, we ended up selling things to NASA Ames. I used to love NASA Ames. They're wonderful, right? They'd come over and hassle me that they could only buy half a terabyte of main memory. You know, they'd say, when are we gonna get a terabyte? You know, I say, well, look, you know, we designed for that. In about 6 to 9 months, the price would be something sensible. Do you have the budget? Oh, yeah, yeah. Okay, then I asked 2 questions whose answers I knew. The first was, will a terabyte be enough? And they said, no, we still can't simulate whole airplanes, blah, blah, blah. You know, they wouldn't do this, okay. Right? And then I asked the second question, which is, well, how much will be enough? And their answer was real simple. There's never enough. I said, I love you. You're a good kind of customer. Good, thank you. The descendants of those machines, actually SGI still sells some. I think they now go to 64 terabytes of main memory. And NASA Ames can take one of those with 1,000 processors and run a single program on it. Okay, so Amazon Web Services. Now, this partly addresses your question, Ed. It's one of the things that reduces the entry cost. Okay, right? Whether it's them, okay, or our friends are from, who talked just before me, is, you know, if you have to invest in a lot of hardware and setup and everything, it's hard to get started, right? Okay, and just as the service bureaus did in the 70s, the web services kinds of entities are doing that right now. They're reducing the barrier to entry for somebody to start small, and they're even giving bigger entities a lot more flexibility in offloading things that they might have to a shared facility. Right? What's interesting is some of the administrative issues are the same things. And what happens when people are sharing a facility. Okay, open source really has gotten going. You have things like GitHub, et cetera, okay? And in fact, that brings me to open source. I'm curious, when do people think open source really got started? 1990-ish?
Actually, GNU software.
Early?
GNU.
GNU.
MIT.
Okay, all right, well actually...
Someone said BSD.
BSD, yeah, okay, so we're talking about 70s. Actually, I claim it goes a lot further back. Okay, whoops, here we go. Okay, well, you know, it's the most recent term for ancient practice. Well, ancient in computing is, you know, 1940s is ancient, okay, right? So, a fellow named David Wheeler at Cambridge invented subroutines. And they started putting code out in libraries where people could share it. Right? A great open source thing was John von Neumann had designed a machine at Princeton, the IAS, right? And that was a time when if you wanted a computer, you had to build it yourself. So a bunch of folks went to John and said, you know, hey, we want to build a computer, you know, how do we do this? He says, well, here, have these plans. So he gave away the specs, you know, for these machines, right? If you come, how many people have visited the Computer History Museum? Okay, well, more you should come, okay? You can see the only one of those left, the Johnniac from Rand Corporation, up in Southern California. It's not something you'd want to maintain, believe it. Okay, right? Wires and stuff over the place. Okay, 1955, IBM Share Users Groups got started. In the 50s and 60s, the open sourcing tended to stay within a single vendor, right? Because every vendor's environment was completely different. The machines were all different. You know, they were 36-bit words. They were 10-character decimal machines. They were 36s, 60s. I mean, there's all kinds of just terrible mess, right? And so there were Share and Deakus, okay, right, were the two biggies. Deacon's put out what was called the Deacon's tape every once in a while, and you would contribute source code to it, and it was always considered, just like it is now, if you put something on there, that was a gold star as a programmer, okay, right? And you got plaudits from people. Yeah, we got your software. It's really good. We like it. Again, programmers always like to write stuff for other programmers that can appreciate how cool they are. Okay. Okay. Now, in the '60s, you might think of IBM open source. Well, that's weird, right? But there was a thing called HASP, which was a user-modified version of some of the mainframe stuff, and it was sort of funny. It was done by IBM people at NASA, but it was so well liked amongst universities and others that a lot of us picked it up and used it. It was, again, an under-the-table project by 3 guys. Right? Most great software usually starts with 2 or 3 people, and this did. But in every share meeting, they would have a HASP user group together, and it was sort of like the way Linus's worked, or the way Ken and Dennis worked, is ideas would come in, and Tom Simpson, who ran this, would sort of bless them or not, but they would talk it over and share improvements, right? And this was all, it was sort of weird for IBM to be doing this, but it was okay with it, right? They got a lot of free labor for it. Okay, now the 360 was really important, not just financially successful, but it created a whole lot of compatible systems, unlike the complete chaos that existed. So I wrote this thing in 1970 called Assist, which helps students learn assembly language and computer architecture, right? And it got used by about 300 universities over time, and was actually a version of it still running a couple years ago. Right? By the way, let me give you a warning. Be very careful where you put your name in source code. Because 10 years later, I had somebody, 10 years after I'd been at Bell Labs, and had nothing to do with it, somebody came to me at a conference and said, "You!" I went, what? Okay, we looked at my name badge. She says, "Yeah, we got Assist Ambend 101, and it said send deck to Mashey." I went, "Oh, geez, I left that in there." Okay. Don't ever do that, right? Could I say? So, let's see, 1970s. Now, UNIX was not open source in the modern term, but certainly inside Bell Labs, it sure acted like it. Okay, early on, a release, a UNIX release was that you drove up to Murray Hill, where Ken and Dennis were. You just got on their machine and saw what was new and made a tape and took it. That was a release. Right? Unfortunately, they wrote really good software. Bug reports, forget that. Okay, right? Support, no way. Computing research never did support. That, right? But the result was that lots of people tried different things. And, after a while, it got a little out of hand. At one point, a department of 20 of us had something like 10 different versions of the UNIX shell. Well, that's probably not a good idea. Okay, right? And over time, there was, also eventually Bell Labs management realized that almost every single project inside Bell Labs depended on UNIX, and there were so many different flavors they didn't know what to do. Right? It was just completely crazy. Okay, so but come later in the later on, UNIX got licensed. The standard license, you've got a mag tape. It said, "As is, don't call us." No. There were problems with lawyers, right? AT&T was not supposed to be in the computer business, so if we acted like we were a computer company, we were in trouble, so they didn't, right? Also, there was a wrestling match forever between Ken and Dennis in research, who wanted to get UNIX out to lots of people, and AT&T lawyers who were very nervous. Right? Actually, the story is that Ken had a friend at a hospital, and he said, "I want to get UNIX, how can I get it?" And he ended up writing a letter to the lawyer saying, "I need to have UNIX here, or you're going to see headlines, 'People die because this hospital can't get UNIX.'" And that finally broke the logjam. Okay. 1970s, John Lyons, a great Australian guy, took UNIX version 6, which was kind of obsolete by that time, because version 7 had come, which was the portable one. And he had 2 books, one of which was just all the source code from the 6th edition, and then a line-by-line commentary. Now, the AT&T lawyers did not like this at all. What was funny is, it was probably one of the most copied books anywhere. Because lots of people copied this thing and they used it in classes. But actually, while the AT&T lawyers were hassling John, we used it as a text inside Bell Labs. Which was amusing, right? Oh, by the way, if you saw the very beginning, I happen to have the California UNIX license plate. And I got that in a very limited auction, as the guy who owned it was moving back to New Jersey. And the money went to the UNIX Association as part of a memorial scholarship for John Lyons, who was very ill and not going to last for a couple of months. So, also in the 70s, Berkeley UNIX, and the internet and DARPA money, all that stuff happened. There's also a thing called the Software Tools Users Group. And the idea here at that time was that people loved the UNIX toolkit, but they, for some reason, had to use some other machines. So they put layers on to try to move the tools over. Right? One of the reasons, and this bears on these stack wars I keep talking about, one of the reasons that they felt compelled to do a portable version of the operating system itself is that the software stacks inside these different operating systems were very hard to put the Unix tools on. Right? People did it, but it was really painful. Right? So you had one of these things where it was easier to move the operating system to new hardware than it was to cope with weirdly different operating system stacks. Okay, so 79, that came out. Okay, so here's, people mentioned GNU. Well, there's GNU, right? Then you get Linux and you get Apache, and it's a lot easier to cooperate, so people share stuff. People have been sharing stuff for a long time. What's changed is it used to be local libraries. Then if you wanted to distribute, it was a magnetic tape. Then you got UUCP, then the internet, and then web and GitHub and so forth. It used to be just local groups who could share, then there got to be vendor groups, and then there was a big expansion for the public and lots of people. Sorry.
Before you had GNU C, how did people share source code? Or did they share source code?
Pardon?
Before there was GNU C, how did people share source code?
Okay, so good question. Before there was GNU C, how did people share source code? Well, let's see. In the late 70s, they took Steve Johnson, as I recall, took the original PDP-11 C compiler, which you definitely knew it was PDP-11, and there had been several ports of that to other machines, right? IBM 360s, which was okay. UNIVAC 1108s, which were 36-bit ones complement machines, UGG, right? Okay. And various other weird machines. It was pretty painful, okay? So, the portable C compiler was done at that point, right? What that did was split the problem. You would then have a fairly large body of C code that, if it was at all carefully written, all you needed was a C compiler on a machine and things would work pretty well.
Yeah, but the point is you get a tape or a deck of cards
Yes.
to get the code right. How do you physically do
Oh,
that?
how do you physically get the thing? Yeah, it'd be a tape, You'd send tapes around. My wife reminds me, right? It would not be a deck of cards, Angela. No, Unix never lived on cards, thank goodness.
No, but I punched out cards in the computer center at college.
Okay, but that was before that. Okay, all right, well, okay. So, I don't know, does that answer what you were asking?
How much grief was involved in compiling some of the source code?
Okay, how much grief was
Are
in...
you talking like 10 minutes or 10 weeks?
Oh, okay, well, so the question, so it's actually a very interesting question in portability, okay? How much grief was involved in moving, say, to a new machine? Is that a fair question? Moving somebody else's code. Early in the game, okay, where the big transition kind of happened is when the Motorola 68000 chips got going with early workstations, okay, right? Because they were the opposite byte order from the VAX, and the VAX was the dominant machine that universities used and everything. And among other things, because of the opposite byte order, there were sometimes little unportabilities in code, and something would just break, and it would take a while to figure out. What happened later on was that people got pretty good with coping with different variations. And you would find, for instance, that a database vendor would come to you and you'd say, okay, we want a port of your database on our system. And they'd say, okay, what's the byte order, how many bits, blah, blah, blah. And they'd have if-defs, right? It'd all be parameterized, okay? But that took some years, right? But after a while, people, you know, developed default rules on, hey, code this way, don't do this other stuff, right? So it's not like there was one time where magically something changed. It's that good practices spread. Look, in the early 70s, the idea that you'd have what looked like the same operating system running on radically different hardware was crazy. Nobody believed that. Okay, well, at the early time, they all thought systems code had to be written in assembler. You know? And C was looked at as some weird thing. You know, and so it tends to be a more gradual process. Certainly, by the 80s, well, Bell Labs had a good deal going in that many students had learned on UNIX machines by the time we could hire them. Right? That's both good and bad. They came in knowing UNIX backwards and forwards, but they also didn't quite have the experience in dealing with completely different environments. So, does that answer you? Yeah, sorry.
How much of the code sharing is done by email or by bulk or by physical shipping of the new?
Okay, so the question is how much sharing was done by email or whatever versus shipping a tape? Is that a fair way to say? Okay, well, let's see. So late 70s is when UUCP came in over dial-up lines that copied files around, okay, right? And before that, it was pretty much tapes. It's pretty ugly, right? Then UUCP got to be around and robust enough that you dare use it. Went through a couple iterations. That project, that data mining project, we did. We actually developed something that looked like the same nomenclature that you find in URLs. Okay, right? We bundled up all of that. Whenever we did an update, we bundled all the documentation together because it had names just like programs. And UUCP them out to the Bell system customer. They'd unpack the stuff. It'd all install all that stuff. So that sort of happened. I'd say the electronic distribution started to happen in the late 70s. You know, it's still, a lot of cases, literally over you know, dial-up phones, okay? Phone lines. So it was kind of like not very fast.
So I have a quick question.
Sure.
So success of computer industry always related with the operating system.
Yes.
In 70s, 80s, the popularity of UNIX, right?
Yes.
Starting from 90s and 2000, even now, the popularity of Linux. What's your vision about the next generation operating system in terms of big data, cloud computing?
Okay. All right. Well, so there's at least a couple parts of this question. One part is, so hey, it was Unix in the 70s, and now it's Linux. Okay, right? Okay. I'm an old guy, right? I have Linux penguins in the back of my car too. Okay, right? You know, there's man pages in Linux that I wrote a long time ago. You know, some things are different, and some really good added stuff has happened. In a lot of cases, it re-implemented the same syscalls and all that sort of stuff. Okay, right? So my model of the world tends to be. You know, if it looks like a Unix more or less and acts like one, it's one. Okay, right? So I consider, you know, Linux is just, you know, an open source version with a different model, you know, and it's otherwise pretty comfortable.
You know, from mainframe to client server,
yeah.
Right now it's cloud.
Yes.
Which means cluster of nodes. I mean, the operating system must have to adapt the architecture of network, you know, or computers, you know, for sure.
Yeah. So here we go. Yeah. Computers have to adapt to networking.
Software adapted to hardware, right?
Yeah. So here's the thing. This is why I've kind of emphasized this business with the clouds that appeared earlier. Right? People have had to work on networking stuff for a long time, right? And sometimes it's been retrofitted in ways that aren't too pleasant, but it's been there. Okay, right? And so the other thing is, once something gets in place, it tends to last a long time, which is what I'm going to come back to. So let me finish up here shortly. Okay, here's the 30,000-foot view. I'm not going to try to tell you, because you know better than I, which chunk of which stack is going to win. Okay? All right? What I want to do is talk about what happens and when things happen. You know, whenever there's been big hardware discontinuities, the market changes a lot. There's lots of opportunities. Things come, things go. All right. Many computers came along and eventually wiped out the mainframes. Some of them, microprocessors just completely blew the mini computer guys away. Networky stuff, you know, made a big difference. But then after a while, some parts of this settle down, right? But sometimes there's turmoil periods in some part of the stacks that people use. Which is why, again, I think VCs are investing again in enterprise stacks, right? Because there's stuff to do. So some things are pretty predictable. Moore's Law for CMOS, well, we still get a couple more rounds, but it's getting pretty hard, right? You know, they're working like crazy on other technologies, but we've been on a nice ride for 30 years or so, where you could keep shrinking the transistors and getting more stuff, and you had to work harder at it, but it was sort of familiar, right? For a long time, the smaller transistors ran faster. It was wonderful. You shrink, you get more chips on the on the wafer, and the transistors switch faster. You get an automatic 50 or 100% improvement in clock rate. Well, you notice that's gone, right? I mean, you know, getting faster clock rate every time. What you get is more cores, right? Because you do it in parallel. The problem is, at this point, the delay isn't the transistors, it's the wires, right? And you just don't make them, they don't shrink, they don't go as well. So, what this means is parallel programming at every level is more important, and certainly multi-core, we keep seeing that. Certainly something that's become much more important than in the 80s is power and heat, right? You know, you talk to chip designers these days, and they have to stand on their heads with power issues and chips that would melt if you ran them full blast. And things like turning cores on and off dynamically depending on who's hot. Weird stuff, right? Disks keep getting denser. I think that's going to go on a while. But the bandwidth, you know, the density is like a square, and the bandwidth improvement is on one side of it. It's like the square root, sort of. And the seek rotation times, man, that's just stalled, right? So you can have a lot of data out there, but if you try to access a whole lot of it, it's not very fast. Okay, network speeds, I think that's going to keep going up. There's huge markets there. It's getting hard, but you know, we'll get there, get further. Okay, and some of these effects are things we've known about, and you keep turning the crank and they keep happening. Now, interesting things that are predictable, but may have hard to guess side effects would be, you know, the whole Internet of Things and wireless sensor networks, and everything has an IP address, and you know, this can get pretty exciting. I helped a company get funded called Dust Networks. A guy named Chris Peaster invented the term smart dust, which shows up in science fiction books. Right? And I had him do a talk for VC Task Force, and then a month later he did it for somebody else, and I was in the audience. And I poked at the panel on security. I said, so let me ask you something. With all these great wireless sensor nets, what is the moral equivalent of spam and viruses? And then they did all their stuff about how good they were, and they fixed all this. And Chris ended up saying, we've done this and this and this, we learned from the internet. But one of these days, you will find that your microwave has sold Viagra to your fridge. So we don't know. We'll see what goes on. I think there'll be surprises. Personal graphics, I think it's Rainbow's Edge. That's the right title. Werner Veen, science fiction author. What happens when Google Glass gets replaced by contacts that immerse you in reality? But I don't know, anybody ever observed Wikipedia edit wars, where people have really strong views of what should be on there, and they keep fighting over it? Well, in this book, it's a Hugo winner, there are different groups of people who fight over the virtual reality they all get to experience. It would be pretty weird, except Werner is on a long track record as a computer scientist of writing good stories that use the most current research and then extrapolate and turn it into stories. All right, a big one though, and I think for big data, is flash memories as more than solid-state disks, right? Anytime you do something substantial to the memory hierarchy, there's opportunities for doing software differently to take advantage of it, right? Now, there are issues there with these things, like 4K byte pages, just like we had in IBM 360s, are bad news, right? They just really don't mesh very well with, I mean, you have to work pretty hard around it. Sad to say, we had some of that stuff done in IRIX at SGI in '96, and some of it got into Linux, but some of it didn't. Not too bad. Okay, so we'll finish up here, next to the last slide. I think that we're in a period of going to be interesting turmoil in the software stacks. We now have tall, wide software stacks that come from multiple vendors that are going to be hooked together. You know, back when I started, the whole stack was a simple OS, compiler, assembler, linker, and a few libraries. That was it. You know, you wrote code. You didn't get it. You know, you just wrote it. You didn't have much, right? So I think there's two things to do. If you're building software on top of some big, deep stack, you want to check your choices pretty carefully. We used to say in the microprocessor business, it was like picking a microprocessor to base your products on was like playing Russian roulette, where you pick, you spin the cylinder, you click, and you wait 2 years to find out if you've killed yourself. Right? And I think that's still true here, because if it turns out you pick something that looks really good, but it never quite makes it, and you have to undo that, it can be pretty painful. Right? So it's really one has to be very careful in figuring out whether something is likely to make it and assessing its maturity. Now, if you're building pieces of the software inside the stack, often the best technology does not win. In fact, quite often what wins is the right alliances and partners that can help you do it. Right? And I think any software company, I hope, has got really good biz dev and alliance folks, right? Because small companies in particular just can't do it all. You've got to work with other folks, right? That's been true through this whole thing. We've had all these wars over all kinds of stuff, right? And you just got to do it. Needless to say, getting some customers sometimes help you get those alliances, right? So sometimes you go make something that's good for somebody and they help you get more. Now, the last thing where I'll end up is that anything that gets enough market share lasts a long time. You know, there are still COBOL programs, right? Yeah. How many people have ever written COBOL? Wow, wow, this is awesome. Okay, right? And of course, there's a lot of Fortran. I mean, there's still a lot of Fortran. Big scientific codes are still done in, you know, Fortran, something or other, right? Let's see. A lot of languages have died off, but you know, so be it. Okay, right? Some have lasted a long time. Nobody in a million years in 1973 would have thought C would have become what it's been, and underneath so much stuff and very different variations. You know, it was a thing that Ritchie was doing, you know, and it was nice to write a little operating system for PDB-11 in. I mean, you know, and nobody had any idea that it was going to get so big. And some of us, you know, glommed onto it, but we never did. So I'm going to end up, for the very far future, going to one of my favorite science fiction authors and favorite books. So this is the last slide. So this is a retrospective from 5,000 years in the future. Okay? The hero, Bam, has joined a starship crew, and he's smart, so they make him a programming archaeologist, meaning he can dig down in layer upon layer of software and understand it and fix it without breaking stuff. So that's what he's learning to do. Okay, right? Some of you may recognize this thing, like, where did this stuff come from? Why did they do this? Okay, right? Well, that's what it is. Okay. So he is appalled by the code that he finds. The programs were crap. Programming went back to the beginning of time. There were programs here that had been written 5,000 years ago, before humankind ever left Earth. The horror of it, these programs still worked. Down at the very bottom was a little program that ran a counter. Second by second, it counted from the instant a human had first set foot on old Earth's moon, you know? But if you looked at it, they were off about 15 million seconds, the 0 second of humankind's first computer operating system. It doesn't say UNIX there, That's what it is. If you add it, it's January 1st, 1970. Okay, you add it up, right? So he says, he's looked at the code, he's discussing this. We should rewrite it all. One of them said, this crew says, that's been done. Somebody else says, that's been tried. You and 1,000 of your friends have to work for a century or so to reproduce it. We got 1 trillion lines of code that we need here to run this starship. So, and guess what? Even if you did, you'd have your own set of inconsistencies, and it wouldn't be upward compatible. Right? And he says the word for all this is mature programming environment. So, to some extent, that's the world all you folks writing software now live in. There's a lot of software around. You depend on big chunks of it underneath you to still work, right? And this sometimes gets pretty exciting when it's a whole lot of it's open source, because you can fix it, but it can take a long time, or you can get surprised by something you think was okay. You don't have a vendor to point at and beat over the head and say, I'm never going to buy anything again, right? So I think that we're in for some pretty interesting times with the cloud stuff has come back and forth. The open source stuff in cloud definitely enables people to get started smaller, and that's really valuable. Right? So I think just as mini computers did that in the 70s, and microprocessors came along and did it some more, this time is one where there's a lot of chance for even small companies to build interesting software. So I will leave you with that. Thanks. Question? Oh, can we just a second? Wait. Can we close the door?
Yeah, sure.
Give out a mic, yeah.
Yeah.
You got
You can use it.
Yeah, lights up. Put it back.
Hello. So you talked about tools. You talked about tools and all of these things. And I believe the tools are the uncontrollable.
Oh, wait. Hold up a second. Go do that.
I wanted to talk about tools as an example of how tools can be annoying, right? So you talk about tools, and I think tools were very important for the success of software development, right? Mm-hmm. So from all these tools we have done or interacted in the past, which ones do you think have the biggest impact on the software development?
Okay, wait. So, do the first part of that question again? Tools.
The tools, right? So you talk about tools, and I think tools are the instant heroes of software success and stuff, right? So from all the ones we interacted with, which one do you think had the biggest impact?
Okay, so if I understand it, like, of all the stuff I've seen, what do I think had the biggest impacts and tools?
What tools had the biggest impact?
Tool sets, okay, all right. Boy, you know, that's hard. That's a hard question. Let's see, but, well, let me think. Just happens, I got a couple more slots. And one or two of them may help me. Okay. This was from this talk from a while back. Let's see if we got this. This is a really nice looking little feature, and it grows up into this. Creeping featureism. You ever heard that phrase? Yes. Okay. I actually coined that a long time ago. Okay. So tools. So this was my model as of 1977. Right? Was that let's see. We were getting tools, including a UNIX environment. We were getting things like compilers, which helped us do new languages quick. We had lots of programs around. I had done all this work to turn the UNIX shell into enough of a programming language to automate procedures, right? And we had various ways to hook some of this stuff together. And what my observation is that if you have the crucial thing is to have an environment where you've got lots of little to medium-sized things, not one huge all-encompassing thing that in order to change anything, it's really hard. okay, right? I mean, to me, it wasn't any one tool as much as environments in which you could build things and hook them together and automate them and do all that. Okay? I mean, there were lots of tools, like, I mean, you know, source code control systems originated in this project back then, okay, right? Back around 1973 and 74 between my office and the one next door, right? SCCS is the ancestor of about any of them, okay, right? Long gone, but it was an ancestor, right? It's hard for me to point to any one thing. Again, I tend to think the things that really make the big difference are in environments where you're rich in terms of software you can just use and know it'll work, and you can find it. I spent a lot of time later on with a development environment called Solid, where the issue was, it's nice to have lots of stuff, but if you can't find it, then what good is it? Okay, right? And people would often spend more time writing things than they would organizing them so you could find anything. Mm-hmm. So I don't have a simple answer to that question. I don't think there is one. I think for sure, you know, a really major effect on the computer industry was making UNIX portable, because this was another one of these lowering the barriers to entry thing, because a whole lot of microprocessor-based companies could just do a UNIX port and already have a whole lot of software. So it wasn't any one tool, it was sort of the environment. Sorry, I'd love to say one tool, but I don't believe it. Any other questions? Sure. Here.
I mean, for a development environment, all the tool has its own purpose. If you miss like one tool, you are going to have a lot of pain.
Yes.
So like, for example, debugger, right? Stack analyzer. If you don't have it, so you are going to miss it during the development.
Oh yeah. Well, if you're writing code,
Yeah.
I mean.
All the tools serve the purpose. You cannot say, you know, which one is more important.
Right now, but I was looking in the past, like back in history, like we translated.
Not Emacs.
Yeah, not Emacs. Okay.
Yeah.
Yeah. Well, again, you know, it's different ones for different people. For some people, the truly desperate need that they had to have was parallel debuggers that would debug a 100 processor kind of program and find the race conditions. I mean, you know, if you don't have that debugger, you're dead. Okay, right? And things have come a long way there, but sometimes I think not as far as they should. But, you know, the thing that makes me happiest was that I spent a lot of time saying, whatever you do, program at the highest level of abstraction you can, and then be ready to rewrite stuff at a lower level to make it fast. Do enough performance modeling that you know you're not in trouble, but go get it right first, then recode, okay? I put one of my members of technical staff on this thing written in awk scripts, and he wrote up a little library of things to fake up the awk routines, and then we rewrote the high runners into C, okay, right? But, you know, it worked perfectly fine, right? So I'm very happy to see all these interpretive languages running around that burn up CPU time, okay, right? In order to make the programming easier. I mean, that's a big win. But I think it's, you might look at, there was this paper called Languages, Languages, Levels, Libraries, and Longevity. It's an ACMQ magazine where I talked a lot about this kind of stuff. Okay? Observing, for instance, that a lot of languages are dead, you know, before we generated lots of languages for a long time. Longevity, once you get a real winner, it tends to stay a long time. Also, the interesting thing is if you look at levels of languages, there's only, languages and tools, there's only room for a couple to be really popular at any one level, right? So, for instance, they kept trying to make systems programming languages to compete with C, right? And inside Bell Labs, I'd see a memo from somebody, you know, at least a couple times a year saying, C could be better if only we did this and I've implemented it, okay? It would be 5% better, but it would be different. So they all failed. And I think that's one of the things you see is for things to exist, for coexist for a long time, they really have to do different stuff. Sorry.
How would you assess the contribution or the damage, either technically or politically, of Richard Stallman and his little gang of socialists there?
Okay. How would I assess Stallman and Company? Let's see. So, let me think if I could do this in a concise fashion. I once spent an hour on the phone with him. What we were doing.
Commendable endurance with him.
Right? Yeah, I know, it's a long time, okay, right? The issue was, we were doing this spec benchmarks. All of the vendors who were involved in setting that up, okay, we all agreed there were bunches of benchmarks we used for real programs, not tinker toy stuff, like dry stuff, okay, right? Well, you know what? Every one of us had a benchmark that was a GNU-C benchmark. You know, where we compile GNU-C and then we run something through it and then you do it, okay, right? And all we wanted to do was have a frozen version of that we could put on a tape to give away, okay, right? Or, you know, well, we you know, cost you to get the tape, basically, right? But we wanted a frozen version so that it would be the same fair test for everybody. And it took us an hour to argue Richard into this. So it was just, you know, okay. So I think Stallman's done plenty of good stuff, right? I think the question of when something is open source or not is not one of those things that's a simple answer, right? And they always want it to be simple, or one edge of the spectrum, right? I went through a lot of time last couple of years at SGI, for instance, getting people to put XFS into Linux, as opposed to doing a whole magic special different version of Linux, okay? It was considered one of the family jewels, but if we didn't do that, we were going to be stuck with hassle forever, okay? And I think it contributed to the community, that's very possible. Okay? So, you know, the dogmatic view that Richard sometimes has, you know, is a little far from my taste, because, after all, there are big, important software packages. And I'm sorry, you are never going to get to support in an open source fashion. Right? I just don't believe it. Okay, right? Lots of kind of things that works very well for it, right? But if I look at, say, the McNeil Schwindler code for mechanical engineering, which builds bridges and stuff, people want a vendor there, okay, right, that will support that and make it get the same answers on different platforms. SAS Institute is another one like that, right? SAS Institute, you know, started on IBM mainframes. They've got James Goodnight, is the CEO and owns, you know, a big chunk of it. He's a pretty wealthy guy. But he, at least when I met him, you know, 10 years ago, he was still writing some code now and then just for fun. Okay, right? But they do stuff where they have to get floating point computations across a whole range of machines to get exactly the same answer. It is hard work. Okay, right? There's a whole lot of testing that organizations have to do for certain kinds of customers. And it's hard to see how you quite make that work in an open source environment, right? So I went through at SGI, we were trying to figure out for each chunk of software, is this something that we should in fact keep proprietary? Was this something we should open source? Because open sourcing was never free. It took energy to package it up in a proper way. Right? Is this something we should spin off into a separate company where it was something that could be a product on its own, but it didn't fit the rest of the stuff we were doing. And there were things like that, right? So anyway, you know, I've been on all sides of the open source versus proprietary stuff. I think there's plenty of roles for both. I'm generally happy that there's more open source around. I mean, you know, the way I learned C was I got the 20-page memo from Dennis and then looked at lots of code. That was it. Okay, right? That's how you learn back in 1970, because there wasn't anything else. There was no K and R, C book. I mean, there was none of that stuff. Right? So I don't know if that answers it. I mean, but it's like, hey, lots of good software was done in there, but you know, sometimes the intense belief in just one end of the spectrum, I think, gets a little crazy. Any others, sir?
In your opinion, which layer is the most old-fashioned or hassle to accelerate big data business, like server, storage, operating system, or data analyst.
Okay, so if I get this right, which area is best for accelerating data, big data?
Yes.
Okay, and it was server hardware, right? So, right, servers, operating systems, and what else?
Or storage or network.
Networks, okay. Well, okay.
Storage.
So the top level answer is that it's never any one thing, right? I mean, part of the issue that I tried to address early, and in the full-bore hardware or software talk, is you can be terrifically good in one area, but if you're lousy somewhere else, yeah, you know, it doesn't matter. You're always held back by some limiting factor, okay, right? Now, so the way I put it is, my top couple things that I think make a big difference is, I do think operating systems, Linux and otherwise, need substantial scalability work, not in terms of number of processors so much, as in how big pages are, okay, right? I mean, there's an awful lot of 4K page stuff that's still around, okay, right? And we had to deal with that years ago, okay, right? I mean, I hassled the MIPS chip designers to give me variable page sizes going from 4K up to gigabytes, okay, right? Because sooner or later, you just can't map enough memory. You know, you spend all your time thrashing around, okay, right? Especially important for these for these things that are flash memory that look more like real memory, maybe. You know, the trouble with those things is that the time to write something is a long time, and you can't just write a few bytes out there or even a 4K thing. You got to erase and then rewrite the whole thing, right? So I think to some extent we're still living with a 4K byte page idea that's long past its due date, right? And there are some kinds of things that just it's really hard to fix without getting that from that, right? Now the other thing though is, I mean, look, this feels to me right now a whole lot like it did in the early 90s with parallel programming inside the same machine. Parallelism is hard work, right? You can get all kinds of funny bottlenecks, right? And early on, you need really wizard programmers. Later on, you get to automate that. You know, automating and being able to use parallelism in more applications is a huge win. It's just hard work. Right? I think network stuff, knowing what's going on in the network and being able to understand it is something we got to work on real hard. Okay, right? I mean, like if Amazon Web Services suddenly gets slow, well, why is that? Right? I tell a story here. My favorite one. Well, let me see. Do people remember what happened with the net? Either of two times. There was a time when Intel put up a URL in the middle of the Super Bowl, and next thing you knew, everything was slow. Right? That was one. The other one was the first Victoria's Secret fashion show via the net. Okay. All I know is things got real slow about that time. You know, it's hard to know what was going on. Okay, right? And the trouble is, if you want, you know, service guarantees, okay, right, and you need that. Sometimes cloud stuff can be hard, right? The classic thing we worried about this in the Bell system, of course, because we owned the network, right? The classic one would be what happens. It was called the Boston Astrologer Syndrome. Right? The Boston Astrologer Syndrome happened like this. Once upon a time, if you made a phone call, you went to your local switching office. It went up a hierarchy, okay, of switches, till it got to as far up as it had to. Then it came back down switches to somebody else, and you had a phone call. And when it did this, at each step, it tied up equipment, because this was circuit switch, it's not packet switch stuff. Okay? So you would go up, and then you'd come down. Okay? All right. Now in Boston, the top edge of that was around New England. The top end is in Boston. Okay? And if you were going to do a radio call-in show, you were supposed to arrange with the phone company beforehand, and they'd set up some special stuff so you didn't get swamped. They give you special numbers. some astrologer apparently blurted out, well, if you want your horoscope, call this number. 30 seconds later, New England was down. Right? Because all these people started calling up. They all headed to Boston. It started tying things up. It wouldn't find out it couldn't go anywhere until it tied up everything. Okay, right? Now later, the switching machines got a lot smarter, and they would give you, ever get a fast busy? You pick up the phone and meaning, hey, I can't go anywhere. Just don't bother me. Okay, right? We didn't have that then. Right? But you know, I see analogs of that in networks all the time. Particularly, the more complicated they get, and the more dynamic and the more wonderfully load balancing and sharing can be done, the trickier it is. Every system I've ever seen that was dedicated, you knew what it did. But every time you could share between things that have varying workloads and stuff, you had to work harder to keep it performing well. Right? And we got, SGI used to do real-time stuff. Well, people did real-time versions of UNIX and everything. We just gave up and said, here, you have a multiprocessor. That one right there is dedicated to being a quick response for this event. You can make that work. So anyway, I think the bottom line, though, is I think there's action in a lot of different things. Okay, right? I think that these days the server stuff is mostly driven by what the chips do, and they are what they are. Okay, right? And they'll keep cranking. They're likely to get more parallel, because they're certainly not going to get higher gigahertz. IBM's gotten to 5 gigahertz with its Mongo chips, but those are really pushing on the edge. So, anything else? Okay, well, thanks for coming out and staying so long.